Adam Rees on the universe and our comprehension of it. Barring the estimation mistakes, there remains the genuine and invigorating chance that we have misjudged the universe. A Nobel Prize winner warns us that the James Webb Telescope shows us evidence that something odd is happening in the universe. If we trust the latest measurements from the James Webb Telescope, our universe would have moved in such an unusual manner that there is simply no obvious explanation for it. But what would that mean in tangible terms? Are we truly powerless against the latest developments? Or do we perhaps already have another explanation? Adam Rees is one of the leading cosmologists of our time. Years ago, the Nobel Prize winner presented groundbreaking work on the expansion of the universe and discovered disturbing errors in the measurements of the Hubble constant. These differences from earlier measurements became known as the Hubble tension. Rees, along with thousands of other scientists worldwide, eagerly awaited the launch of the James Webb Telescope. The new technology would finally provide proof of the true nature of the universe. Answers to questions such as whether Rees's measurements were wrong, or if the older measurements were inaccurate, were expected to finally bring us clarity. Of course, it was also possible that the Hubble tension was a previously unexplained phenomenon, but no one wanted to face that reality at the time. The Webb telescope stunned scientists because the latest measurements confirmed the accuracy of all prior measurements, thus ruling out a pure measurement error. Increasingly, the differences in the measurements certainly don't occur, because our telescopes measure inaccurately. Hubble and Webb each made two measurements, one using Cepheids as standard candles, and one using Type 1a supernovae. In this context, standard candles are measurement constants that scientists use to achieve precise results in the universe, using the absolute brightness of these phenomena. Essentially, both measurement methods should show similar results. What was measured was the expansion of the universe, or rather, the rate at which the universe is expanding, and whether it's accelerating or decelerating in the process. Minor measurement differences would have shown a variance in the absolute brightness of the standard light, and that would have been scientifically plausible. However, the difference is so great that Adam Rees suspects the Hubble tension is pointing us toward other fundamental misunderstandings about the universe. Adam Rees and the discovery of dark energy. Did you know that Adam Rees is the father of dark energy? In 2011, Rees shared the Nobel Prize in Physics with Saul Perlmutter and Brian Schmidt. The three scientists were honored for their remarkable discovery that the universe is not only expanding, but is doing so at an increasing rate. This realization also shocked researchers because, in reality, the universe should be slowing down. Imagine the Big Bang as an initial burst of energy, after which the universe races off, forming matter and occupying an ever-expanding space. According to our current physics, it should eventually slow down. This concept, that the universe would eventually run out of steam, so to speak, led to the Big Freeze hypothesis, in which the universe will end in a state of shock when all energy is spent and all processes cease. However, the measurements taken by Rees and his colleagues showed that the expansion of the universe isn't slowing down, it's speeding up. But how is that possible? This counterintuitive truth led to the introduction of the concept of dark energy. This mysterious force, which no one has yet seen or measured, is thought to be responsible for the accelerated expansion of the universe. The James Webb Telescope confirms Rees's hypotheses. To confirm these theories, the Hubble Space Telescope was used before the launch of the James Webb Telescope. Adam Rees works not only as a professor of astronomy at Johns Hopkins University, but also at the Space Telescope Science Institute, which oversees the Hubble Space Telescope. In the 2 years since its launch, NASA's James Webb Space Telescope has already shown us numerous phenomena that confirm Rees's hypotheses. These include galaxies so old that they shouldn't even exist. Additionally, there has been no sign of a dark age or real relics of the Big Bang. Thanks to Webb, we can observe clusters of galaxies that are so massive and so large that they challenge the theory of an isotropic universe. This, along with the phenomenon of the Hubble tension, confirms the suspicion that we simply haven't understood the universe correctly so far. These new findings will now potentially lead to fundamental changes in science. A new understanding of the universe, Not only Adam Rees sees that our scientific understanding of the world and the universe is currently facing major challenges. Throughout science, more and more experts admit that increasing riddles in cosmology are forcing us to reconsider revolutionary changes. The universe is a far more complex and enigmatic place than previously thought. Imagine we live in a universe in which no physical constant is truly constant. That would mean Einstein's theory of the speed of light isn't accurate. Standard candles can never produce consistent results, and physics itself changes regionally, or even over time within our universe. Such contemplations arose after the latest measurement results of the JWST. The new theories go even further. For instance, there are approaches that suggest intelligent forces exist in dark matter or dark energy. This would imply that our universe has something like its soul or intelligence, which could explain who or what created the universe in the first place. While we are still far from confirming such groundbreaking ideas, the James Webb Telescope is providing us with evidence that challenges long-held beliefs. We humans have only begun to explore the mysteries of the cosmos, and every discovery brings new questions. Our environmental factors, and eventually the universe, have long fascinated humanity, prompting us to seek answers to profound questions about their origins and purpose. We may now be at a turning point that transforms our understanding so radically it resembles a revolution in knowledge and science. Less speculative theories simply state that our universe is much older, or that it may have no beginning and no end. But where do the signs of development come from here? There are intriguing new ideas suggesting that our universe is subject to regional flows. Imagine something akin to a drifting bubble. Expansion and contraction occur regionally, at different rates of acceleration and growth. If there never was a Big Bang, this perspective makes sense. It is no surprise, then, that no definitive evidence for the Big Bang has ever emerged. For a time, the alignment of theories seemed to confirm the idea of a starting point some 13.8 billion years ago, but no tangible evidence has been found. Looking again at quantum and particle physics, we find further evidence that something is amiss with our old perspective. From the quantum world, we know our universe must be far more variable and flexible than previously thought. Adam Rees, one of the few researchers keeping a composed outlook amidst the upheaval triggered by the James Webb Space Telescope, JWST, acknowledges that nothing in cosmology is as it used to be. Observations suggest the universe is likely much older than expected, galaxies have formed faster, and the universe's expansion may not stem from a singular point. If dark matter remains elusive, the JWST is already unveiling inexplicable phenomena in the universe. Rees, a leading expert in studying the expanding universe, made a groundbreaking contribution to discovering its accelerating expansion. His work altered our perception of cosmic growth and earned him the Nobel Prize in Physics in 2011, alongside colleagues Saul Perlmutter and Brian Schmidt. Rees and his team initially used supernovae as standard candles to measure distances and velocities in the universe. These highly precise measurements revealed an unexpected peculiarity. The universe's expansion was increasing rather than decreasing. This anomaly became known as the Hubble tension, arising from discrepancies between measurements based on supernovae and those relying on redshift data. Today, this tension continues to challenge the isotropic model of the universe, which assumes it appears uniform in all directions when observed on a large scale. The isotropic universe, a foundational pillar of cosmology, now faces collapse. Observations from the JWST are reshaping this assumption. While earlier data, such as the cosmic microwave background radiation, supported the isotropic model, the latest findings suggest otherwise. Galaxies and cosmic structures are forming at rates and scales inconsistent with previous models, indicating that the universe's expansion may be far more complex. These revelations also cast doubt on the existence of dark energy, a mysterious force theorized to drive the universe's accelerating expansion. Constituting roughly 68% of the universe's energy content, dark energy was inferred from supernova observations and large-scale structure studies. However, the JWST's detailed exploration of the early universe has unveiled anomalies that challenge this concept. For instance, the discovery of highly developed structures earlier than anticipated suggests the universe may have expanded much faster, or begun much earlier, than the Standard Model predicts. David Gross, a prominent theoretical physicist and Nobel laureate, sees this crisis as an opportunity. Gross, known for his work on the theory of strong interactions and string theory, emphasizes that the answers to cosmic mysteries may lie in the microcosm. He argues that the fundamental principles governing the universe should have counterparts in subatomic domains. Gross's insights illuminate the early moments of the universe, when no stars or objects existed. For millions of years, the universe consisted of a hot, primordial soup where particles moved freely without forming bonds. Understanding these early stages could help unravel the discrepancies revealed by the JWST and lead to a new cosmological paradigm. While the search for answers continues, we stand on the brink of a transformative era in science. The JWST promises to deliver unprecedented insights, enabling us to piece together a more comprehensive picture of the cosmos. Until then, researchers worldwide are grappling with the profound implications of these discoveries, striving to make sense of an ever-evolving universe. The further away the probes are from Earth, the more exciting, but also the more difficult the mission becomes. It is already a miracle that we can stay in contact with technical devices that are so distant. The second critical point is the energy supply. The plutonium-powered radioisotope generators on board the probes produce less and less power over time. The mission teams have already turned off many of the instruments to conserve the remaining energy for the most important scientific missions. NASA is currently hoping that both Explorer probes will continue to transmit data for the next 10 years, and maybe beyond. However, even when the radio connection is long gone, the mission won't end. The Explorer twins will then become ambassadors for our civilization and culture. Each probe is equipped with an incredibly reliable golden record on board, which contains sounds, pictures, and messages from Earth. In many years, the probes might be captured by the gravitational pull of a star, and then appear on the radar screens of another civilization. Explorer, fast, modest, solid. It's hard to believe, but these two veterans of space exploration were put together in just a few months on a small budget to take advantage of a special window in the star system of the outer planets. Saturn, Jupiter, Uranus, and Neptune had not been so well aligned for many years, and it was known in the 70s that it would take another 170 years for the four outer planets to line up again. So they took action and built the two Explorer probes on the fly. Both were to take slightly different paths, and if one was lost, the other would still be there. Eventually, both reached their target. 1977 marked the beginning of a great journey. To accelerate, the two probes flew several slingshots around planets. Explorer 2, launched on August 20, 1977, reached Jupiter on July 9, 1979. Explorer 1, which followed on September 5 of that same year, reached Jupiter in March 1979 and provided the first amazing pictures and significant information about the giant planet and its moons. One of the most remarkable results was the discovery of volcanic activity on the moon Io. At the time, this was the first observation of volcanism outside Earth. After the successful flyby of Jupiter, Explorer 1 continued its journey and reached Saturn in November 1980, revealing the complex structure and beauty of the planet. Saturn's rings, providing interesting insights into the planet's environment and moons, as well as the primary detailed view of Titan, Saturn's largest moon. Explorer 2 examined the perspectives around Jupiter that Explorer 1 had missed. Together, the two gave an ideal image of the gas giant, with so many pictures that researchers still rave about today. Explorer 2 visited Saturn and continued its unique journey to Uranus and Neptune. During its flyby of Uranus in January 1986, Explorer 2 discovered 10 new moons and 2 new rings around the ice giant. The journey ended in August 1989, when Explorer 2 became the first spacecraft to pass by Neptune and send us the very first picture of the planet. Explorer 2 discovered Neptune's great dark spot, numerous clues about the most violent storms in the solar system, and previously unknown moons. After providing significant insights into the outer planets, the Explorer spacecraft continued their journey beyond the limits of the known solar system. Their mission was extended to an interstellar mission, and NASA was astonished at the persistence and reliability these two critical probes had displayed. Until that point, no one had initially believed that the two would ever reach the boundaries of the solar system. Yet they did, and scientists are very grateful for these moving moments. The first time in the heliosphere was a cause for celebration. Explorer 1 reached the heliosphere in August 2012, the vast bubble in interstellar space created by the solar wind, the flow of charged particles emitted by the sun, that surrounds our solar system and protects it from cosmic radiation. The boundary of the heliosphere, where the solar wind meets the interstellar medium and loses speed, is known as the heliopause. Beyond this boundary, the impact of interstellar space begins. Contrasted with the immense vastness of the universe, the heliosphere is just a small speck. However, it extends far beyond the outermost planets of our solar system. Explorer 1 was the first spacecraft to cross the heliopause and entered interstellar space in 2012, around 121 astronomical units from the Sun, equivalent to about 18 billion kilometers. Although this is a large distance from our perspective, it's small compared to the size of our universe. The Milky Way has a diameter of around 100,000 light-years, which is equivalent to 6.324 million galactic units, and our Milky Way is just an average-sized galaxy in a universe that is home to billions of others. So the boundary of the heliosphere is really just a tiny dot in cosmic terms. But for our science, it was a huge breakthrough that revealed some surprises. Expected results were the reductions in the solar wind and the increase in cosmic rays from outside our solar system. Unexpected, however, was the discovery that the magnetic field outside the heliosphere was stronger and arranged differently than anticipated. Explorer 1 experienced a magnetic field more than 4 times stronger than the magnetic field inside the heliosphere. This discovery raises entirely new questions about the structure of interstellar space and the interaction between the solar wind and the interstellar medium. Another surprising result was the discovery of a magnetic highway at the boundary of the heliosphere. In this region, charged particles flow back and forth between the heliosphere and interstellar space, indicating a more complex structure of the heliosphere than previously thought. An amazing stream of particles appeared after crossing into interstellar space, adding further mystery. Some researchers even suggested that we may have encountered the first hints of a new force of nature, or perhaps discovered an alien signature. With each puzzling discovery that scientists make in the Milky Way, we become more aware that we are still far from unraveling all the mysteries of our home galaxy. In the past, scientists have come across several fascinating and puzzling objects at the center of the Milky Way, things that are still making prominent scientists scratch their heads. Anomalous glow at the center of the Milky Way. The Milky Way is known to have a great many shimmering celestial objects, with around 400 billion stars estimated to dwell in our home galaxy. We quickly fall into the realm of mystery. However, not every radiant structure in the Milky Way can be easily placed into a known scientific context. Scientists are also aware of this fact, which is why they are eagerly working to unravel the mysterious glow at the center of our local spiral galaxy. Huge explosion. There was probably just a sort of quantum variance in which all structures counteracted each other in such a way that, according to an actual perspective, they added up to zero. With the enormous detonation, this quantum vacillation self-destructed, and particles loaded with charges and powers shot into a generally unfilled space. These particles later became stars, systems, planets, and living things like us people. It's gross, right? When he says that these particles are the solutions to every one of the inquiries, Presumably yes. But how would we concentrate on the behavior of particles that were in space 13.8 billion years ago? In addition to other things, specialists use the cosmic microwave background radiation. This is viewed as a decently accurate impression of the events not long after the Big Bang, and has probably not changed much from that point forward. Anyway, quantum physicists and traditional physicists don't exactly settle on the best way to interpret this engraving of the good old days of the universe. Right now, the situation in science is that quantum and molecule physics can't be accommodated with traditional cosmology. The findings from the world of formed matter don't fit with quantum physics. Or rather, the limiting connection is missing. David Gross is convinced that this bridge can be found in previously unknown particles and powers. He was one of the specialists who attempted to reach an agreement between the disciplines, even before the discussion set off by James Webb. As co-author of string theory, and in a sound unification of quantum mechanics and general relativity, he was quick to close the gap between the two worlds and disciplines of science. Gross's work on asymptotic freedom describes how quarks act at extremely high energies. This is major to understanding the early universe, soon after the Big Bang, when energies were incredibly high. His theories can explain at least some parts of the expansion of the universe. However, there is some discussion among scientists, as the propositions of string theory are too far-fetched for some old-school physicists. David Gross suspects that the solutions to all unanswered inquiries lie in the quantum fluctuations within the microwave background. The CMB fills the whole universe and can be viewed as entirely surrounding us. The vast Foundation Adventurer satellite, which was active from 1989 to 1993, was the first to see minuscule variations in the temperature of the radiation. From 2001 to 2010, the Wilkinson Microwave Anisotropy Probe explored to track down proof of the Big Bang in these changes, and most recently, the Planck satellite gave one of the most detailed maps of the CMB. Anyway, there is still conflict among scientists concerning how this data should be interpreted. While some claim to have found the fundamental proof for the Big Bang in the CMB, what happened to Explorer 1? As per NASA, the test is conveying a strange message from interstellar space. Could this be the first sign of an encounter of the third kind? Or are we just dealing with a technical failure? Never before has a test been in interstellar space. Explorer 1 is the first man-made object to send information from that point. And it's puzzling. Imagine a scenario in which the interstellar medium is entirely different from what scientists thought. Will we then need to change the textbooks and prepare ourselves for more revelations that challenge our imagination? Imagine how a daring test has been going through space for over 40 years and has now wandered far beyond the limits of our solar system. Then, unexpectedly, the test starts to send a strange and puzzling sequence of signals to Earth. Explorer 1, the first man-made object from Earth, communicated a weird sequence of ones and zeros to Earth nearly 50 years after its launch. What had happened? The binary code was designed in a pattern that made no sense to the researchers. All at once, the NASA researchers and specialists were faced with a riddle. Had Explorer encountered something bizarre, or was the test just broken? The next issue was how to diagnose and fix a problem when the device was 24 billion kilometers away in interstellar space. The situation surrounding Explorer 1 has given NASA many challenges. When the NASA control team first learned of the unusual signals from the Explorer 1 test, the frantic search for solutions began. They began to analyze the structure of the puzzling messages, hoping to find in the pattern a clue to the underlying disturbance. The issue seemed complicated, so the NASA team turned to artificial intelligence to help them sift through the data patterns using a specific algorithm. The AI became an essential tool in interpreting the signals. After months of intense data analysis, a repetitive pattern was recognized, and this was the first indication of a breakdown in the probe's communication equipment. The team developed a theory that a flaw in the telemetry unit, the device responsible for converting and sending data from the probe to Earth, could be the cause of the distorted signals. The next test was to find a solution to fix this flaw remotely. To understand the technical details, engineers recovered ancient diagrams from the archives. Some of the data had long since disappeared or been destroyed, so even retired NASA engineers, who had long since left the agency, were brought in to help solve Explorer's problem. After several recreations and tests, the team settled on a solid strategy. They attempted to instruct the probe to switch to a previously unused communication system that had long been programmed as a backup for just such emergencies. This action was risky because this maneuver could have spelled almost certain doom for communication with Explorer. Then, a mission of a century could have ended sooner than anyone had hoped. Holding their breath, the team sent the command to switch over the communication systems. Then the long delay began. Because of the enormous distances involved, a signal now takes more than 17 hours to reach the probe, and an additional 17 hours to return. We can all imagine the tension in NASA's control room, and the joy when Explorer 1 responded. It was a moment of team relief and satisfaction that will go down in NASA history forever. The spacecraft had successfully received and carried out the command, and the data began to flow again in a clear format. The mission could continue further into space than ever before. It's otherworldly. The solution to the issue will give us years more of data from a space that has not yet been explored. Explorer offers us the unique opportunity to gather information from the endless space between the stars and planetary systems. For the first time, the Explorer mission is truly one of the boldest space exploration missions we humans have ever launched. The primary scientific goals of the Explorer mission, sooner rather than later, include the ongoing exploration of interstellar space. Explorer 1 and its sister craft Explorer 2 are the only man-made objects that have ever ventured into this uncharted domain. Scientists agree that there is a very massive black hole at the galactic center of the Milky Way, which they have named Sagittarius A star. However, in that central region, researchers also found a high-energy gamma-ray shine, which scientists refer to as the GeV excess of the galactic center. For many years, astronomers have been trying to understand the origin of this puzzling phenomenon. One of the most exciting and controversial explanations is that the mysterious gamma-ray shine could be generated due to the destruction of dark matter. However, research published a few months ago by a group of astrophysicists may now put this controversial theory to rest. In their work, the researchers made a simulation model that dealt with the gamma-ray spikes in the center of the Milky Way. The scientists concluded that the destruction of dark matter as the cause of the ominous shine can be virtually ruled out. Most likely, the biggest issue that arises with such studies is the fact that the presence of dark matter has yet to be proven. Undoubtedly, within the ranks of scientists, it's still a hypothesized form of matter, with the help of which the movements of visible matter can be explained. However, the study results published by the University of California astronomy team now shake this theory to its core. The gamma-ray glow, the GeV excess of the galactic center, was first detected when the Fermi Gamma-Ray Space Telescope began taking a closer look at the corresponding central region of the Milky Way more than 10 years ago. It was during these scientific surveys that researchers finally noticed the puzzling gamma-ray shine. Gamma rays are the most energetic electromagnetic waves in the entire universe. The rays are primarily produced by great celestial bodies, including so-called millisecond pulsars. These rapidly spinning neutron stars owe their name to the fact that their rotation period is under 20 milliseconds. Additionally, exploding neutron stars, supernovae, and black holes have been identified as sources of gamma rays before. However, when scientists assessed the data provided by NASA's Fermi telescope, they couldn't pinpoint the source of these high-energy bursts. If we look at the statements of the Italian nuclear physicist Mattia Diro, we realize how much researchers disagree on this controversial question. According to the investigation by the Italian physicist, the source of the GeV excess is linked to interactions with dark matter, as previously mentioned. However, it is not feasible for us at present to directly prove the existence of this hypothesized form of matter. Everything that suggests its presence are gravitational effects that cannot be explained by the impact of visible matter. For example, Galaxies rotate much faster than they should be able to, from a purely material perspective. Thus, scientists are firmly convinced that the vastness of the universe is permeated by an elusive form of matter that causes the otherwise peculiar gravitational effects. Although we can't see dark matter or detect it by any other means, it is believed to make up around 80% of the total matter known to humanity. Scientists Lisa Godino and Dan Hooper put forward the proposal that certain weakly interacting dark matter particles could collide with their antiparticles, annihilating each other. This process should, among other things, lead to the emission of gamma rays into the reaches of the universe. Alternative explanations. Just like with any complex scientific inquiry, this is not the only hypothesis researchers have proposed to try to explain the gamma ray shine at the center of the Milky Way. Around a year ago, another group of scientists concluded that essentially, the impact of unseen pulsars causes the cosmic anomalies in our home galaxy. The fact that we have not yet observed the corresponding old dead stars is simply because they have so far successfully evaded our terrestrial observations in the crowded, dusty center of the Milky Way. However, recent studies have uncovered that the distribution of the GeV excess in the central region of the Milky Way is not uniform. This is peculiar because if the destruction of dark matter particles are indeed responsible for the gamma glow, a uniform explanation would be probable. As a matter of fact, anyway, the gamma ray emissions present themselves in an improved-on dotted structure. Many specialists attribute this to the fact that the GeV abundance would have strong point sources, like pulsars. It didn't take long, however, before this scientific theory was also contested. A group of researchers came on the scene, defending the proposition that the gamma ray sparkle, despite its dotted distribution, could be produced by dark matter. However, the resulting hypothetical models made by other specialists, which looked at the cosmic center alongside the speculative dark matter destruction, painted a different picture. According to them, it is unlikely that the impact of dark matter particles and their resulting destruction are the cause of the GeV abundance. Does this mean, in the converse end, that this dubiously discussed proposition was finally ousted from the ranks of researchers? In truth, that is not the case. The Italian nuclear physicist Mattia Duraro alludes, most of all, to the broad data set of the Fermi telescope, which the specialist uses in his investigations. The researcher looks at data gathered over a representative time period of over 10 years. Specifically, the Italian examines the data gathered by the Fermi telescope with the galactic inconsistencies recorded by the Pamela detector. This was a technical module that had the task of studying galactic rays. The complex gadget, which was attached to a satellite orbiting Earth, was in service between 2006 and 2016. Duraro also includes the results of measurements taken by the alpha magnetic spectrometer on board the Space Shuttle and the ISS. If the abundance of gamma rays were due to the interaction between astronomical rays and atoms, the spatial distribution of gamma rays would be directly linked with the predominant energies. Duraro stated that, as such, there would be a larger spatial distribution at lower energies, while the spread should be much smaller at higher energies. However, the study by the Italian nuclear physicist shows that the spatial distribution of the gamma ray abundance is not connected with energy. Besides, such a situation has never been observed before in the universe, which makes the postulation that it's triggered by the interactions of dark matter more intriguing than ever. The focal point of scientific interest. In fact, most specialists now expect that all dark matter particles have similar energies among themselves. The finding that the overabundance of gamma rays is particularly concentrated in the center of the Milky Way strengthens the theory that dark matter indeed contains a completely new type of particle. The mystery persists about what this particle structure is like. However, it is still quite literally written in the stars. To deeply approach this intriguing question, Duraro, in collaboration with his partner, Wolfpack Winkler, searched for gamma-ray abundances in nearby dwarf galaxies. However, the cosmic search by the two prominent scientists was not met with success. According to Duraro, this situation does not at all mean that their proposal is erroneous. According to them, the research results would rather help limit the potential mass of dark matter particles. As you notice, the current status of knowledge about the actual origins of the gamma glow still seems incredibly diffuse. We can neither prove that dark matter impacts are responsible for this intriguing phenomenon, nor can we prove that they are not. It will likely take a few more years and much more research to make a decisive conclusion about this infinite mystery. Furthermore, up until then, we wait, hypnotized, for new revelations to happen regarding this subject in the future. An unusual void toward the dawn of history may now confirm a surprising prediction by Albert Einstein. Imagine how quite a while ago, scientists slowly began to look beyond the edges of the Milky Way. What they saw astonished them. At first, it was simply cloudy nebulae. Then, of course, these nebulae were different universes. First, the small and large Magellanic mists became visible, then the Andromeda Galaxy. Finally, the stunned researchers realized the number of additional universes there were. Based on these discoveries, thoughts such as the development of worlds and the vastness of the universe were born. Then, Edwin Hubble saw that far-off galaxies were getting away from us, and the concept of expansion was born. Shortly thereafter, the Belgian Georges Lemaitre thought of the Big Bang. This all occurred shortly after Albert Einstein introduced his theories of relativity. Many of the scientific forecasts made during the 1910s and 1920s were confirmed by the new discoveries. However, Einstein was uncertain throughout his life whether the universe truly had a beginning and an end. Although he generally accepted the theory of the universe's origin, he was always sure about another interesting question: whether the universe has a beginning and an end. He was sure that we could never see this beginning and end, no matter how good our telescopes are. How did Einstein come up with this crazy idea? And what does it have to do with the void found by the James Webb Telescope? Albert Einstein's astounding expectation. Einstein was undoubtedly one of the leading physicists of the 20th century, and he made many predictions that are still cornerstones of modern science today. One significant thought was the aforementioned prediction that we would never directly notice, indisputably, the start of the universe. Einstein gave two interesting reasons for this. Firstly, the theory of the Big Bang and other theories based on it hypothesized that there was no light for countless years following the Big Bang. Today, scientists call this epoch the Dark Ages. So, how could we see an event or moment with telescopes when there was no light there? There are even some exciting responses to this question today. For example, radio telescopes. These don't have the ability to hear, but specialists are almost certain that the Big Bang was not a loud explosion, but rather occurred in complete silence. Essentially, the space in which a perceptible blast might have occurred didn't exist at the time of the Big Bang. Space itself only appeared with the Big Bang, and was formed as a result of this event. Radio telescopes detect waves that are typically outside the audible sound range. Space barely conducts any sound. A few other waves enter the interstellar medium, which can be made audible using advancements. We would therefore not exactly have the option of hearing the probably silent start of the universe. We discovered the cosmic background radiation back in the 1960s, and have since studied it very well. This radiation is considered a remnant of the Big Bang, and much evidence for the Big Bang has been gathered from it. However, the microwave background has never directly led us to the Big Bang. So here too, we evidently have no way of identifying or proving the exact start or Big Bang. Moreover, Einstein was also of the opinion that we would never see the entire way to the start or edge of the universe. He was of the view that the beginning would move endlessly further away from us due to the expansion of the universe, and would hence be out of our line of sight. Albert Einstein also believed, at times, in a form of all space. This means that the starting point could also be behind a sort of horizon that will forever obscure our view. Now imagine again that this was when the best telescopes were only capable of obscuring nearby galaxies. Today we are aware of the existence of millions of galaxies in a universe interacting with galaxies, expanding so much and getting bigger and bigger. It may be truly difficult to see far by any means. But that's not true. Despite the vastness of our universe, the spaces between galaxies and galaxy clusters are so large that we can now see 13.6 billion years away with our telescopes. That would be very close to the Big Bang. And with the James Webb Space Telescope, we are already pretty close. But the Webb telescope doesn't show us what researchers call the Big Bang. 100 years ago, the JWST found a peculiar void. I'm sure you've heard that the JWST has found an incredibly large number of very old galaxies that currently even call the Big Bang into question. But did you also know that the JWST has found a strange void that could confirm Albert Einstein's prediction of the non-perceptibility of the absolute? Starting out right, voids are strange spaces in the universe that are so vacant that they really go against the hypothesis of relativity. Yet how might it be that they affirm Einstein's thoughts about the intangibility of the starting? This is at first made sense of by the way that the void was believed to be a sign of the Dark Ages, in which there were very few, essentially no stars and no galaxies. Some scientists accepted that the discovery had essentially confirmed the presence of this APO. But then at that point came the shock. The dimness ended up being an incredibly far-off void. We also know about closer and later voids now. These voids still present baffling issues, but in the very early universe, voids are by and large scientific challenges. They don't fit into the possibility of the homogeneity of the universe, which is directly connected to the possibility of the Big Bang or expansion. Voids are just too big and too abnormal. They have an inhomogeneous character and go against some of the underpinnings of our cosmology. A void doesn't actually affirm Albert Einstein's expectation. Anyway, the Webb telescope appears to affirm the perspective of the brilliant researcher in another manner. The telescope has not really viewed far enough to detect any signs of a start or a beginning phase of the universe. The pictures of the supposedly very early universe, as it were, show designs and systems that don't appear entirely different from those we can observe more closely. Might a void have been the start of the universe? The question now arises as to whether a mysterious void might have been the origin of the universe. We can't totally preclude this, because eventually, we never understand what voids truly are. Nowadays, we also need to admit that we don't have the foggiest idea how the universe truly started. Voids are probably vacant, but we don't know that for sure. Maybe it's possible that they contain matter that we have hardly any familiarity with in one way or another. Imagine dark galaxies. Voids are sometimes interpreted as some kind of parallel universes, and some researchers see them as scar tissue from the crash of universes in the multiverse. Other wild theories claim that aliens obscure the galaxies in a void to reap energy. So you can already see that these strange voids challenge our researchers and lead to the most outrageous hypotheses. Of course, it might be that our universe was made in an enormous void. The simple fact that we can't prove the opposite supports such a thought. That leaves the topic of how matter was made. What are singularities really? We have already discussed the nothingness from which the universe is said to have arisen. If that was indisputably the starting point, how should we notice it? After all, it was nothing, and subsequently not discernible for us. A singularity is a place where all forces are either dense to such an extent that our components of values and sizes fall flat, or all that exists is amassed into this one point, the point comprised of a variance of potential outcomes that existed in a condition of complete harmony. A previously unknown event is said to have upset this halt at one point, and creation began from this little point. Everything that we know and can see today appeared. This implies that in some way, everything, the data for yourself, me, all life on this planet, each star, and each exoplanet, was contained in this minuscule spot of nothing. The question of how an infinitesimally small speck of nothing can contain everything is one of the great mysteries of science. It's unclear whether we will ever be able to solve this puzzle. We find these strange singularities elsewhere in the universe, specifically at the center of black holes. These, in turn, are found at the center of almost every known galaxy, and black holes remain when stars of a specific size detonate. That's what researchers expect. Nobody has ever been at the center of a black hole, and as we have now discussed, we have hardly any way of seeing the absolute starting point of the universe, if it existed at all. Everything depends on computations that made sense until the James Webb Telescope found something else from what our theories hypothesized. The Webb Telescope shows that the universe should be much older than we expected, or that its nature is very different from what all our estimations predicted. An interstellar guest. On October 19, 2017, an absolute achievement was added to the list of galactic discoveries. With the help of the Pan-STARRS telescope in Hawaii, scientists managed, for the first time in history, to identify an object inside our solar system that was labeled as interstellar. As the name suggests, interstellar objects are galactic elements that begin in interstellar space and are not gravitationally bound to a central star. However, this term is also used for those objects that are on an interstellar trajectory but briefly pass into the immediate vicinity of a star. This was also the case with the thrilling body discovered in Hawaii, which was given the official designation Oumuamua. However, when the object was added to the star charts, it had already passed our Sun and was on its way back into interstellar space. The first examination of its orbital properties initially suggested that Oumuamua would be a conventional comet. However, this assumption was soon eclipsed by question marks because upon a more detailed look, the design had no comet-typical tail. This wouldn't remain the only question to follow. In a program where researchers distinguished the first microorganism known to exist on Earth that can mimic using arsenic, this unique bacterium, named GFAJ1, was found thriving in California's Mono Lake. GFAJ1 substitutes arsenic for phosphorus in its DNA and other fundamental cell parts. While scientists still need further research for conclusive findings, the discovery suggests that nature might potentially incorporate arsenic into the biochemistry of organisms on other planets. Maybe it's only too soon for an advanced species like ours to comprehend the ways of nature. Fossil microorganisms demonstrate that life appeared early on Earth, yet how and where it started remains dubious. Living creatures are complex, with intricate systems of genes and molecules. This is a challenge, as even the most basic bacterial cell contains numerous genes and thousands of different molecules. Some scientists believe that before genes or cell walls, the first requirement for life was a metabolic engine. It is key to life, and many scientists believe it was at the core of the first living cells. Once started, these engines could produce the chemicals needed for life, and eventually lead to the self-assembly of cells. However, metabolism is still a very complicated process, which makes researchers wonder, which came first, the chemical engine responsible for building cells, or the cellular systems required to make the engine? In a fascinating experiment, researchers combined 12 compounds in water that are essential for the process called glycolysis. They heated these mixtures to resemble conditions near an oceanic lava vent at a temperature of 70 degrees Celsius for 5 hours, further simulating the early ocean. The scientists added substances like iron and sodium, which were believed to be present during that time. Iron in particular positively affected the reactions. After many years of trial and error, researchers achieved a set of 28 working reactions, including a complete metabolic cycle. Life is incredibly diverse, and the complex cycles of metabolism are just one of many potential systems that can drive the development of life. Could it be that metabolism is only one tool among many guiding the emergence of living things? Perhaps hidden within the vast expanse of the universe lie different parallel pathways, each with its own set of intricate reactions, orchestrating the grand ensemble of life in ways we have yet to understand. There's a possibility that life itself could comprise various combinations of elements emerging from cosmic dust and plasma. Recent studies have confirmed that inorganic dust, including iron, silicon, magnesium, and carbon, displays surprisingly similar behavior within plasma. Under certain conditions, these particles can combine to form complex compounds that allow for interactions like those found in organic matter. Previously, researchers believed that solid particles in cosmic plasma only made thread-like arrangements. However, Through advanced computer modeling, scientists have discovered something intriguing. These thread-like structures can organize themselves into spiral or helical shapes through self-organization. Even more shockingly, researchers have found that these formations can participate in interactions and undergo changes similar to those observed in DNA and proteins. These mysterious helices and twists formed by solid particles can divide or duplicate, creating two copies of the original structure. Through interactions with each other, they change and evolve during this process. The plasma maintains the most stable duplicates while discarding the less stable ones. Far out in the universe, there could be a living helix in a vast plasma cloud, slowly evolving into a much more complex organism. Or perhaps there are nanomicroorganisms inhabiting a neutron star. These creatures, according to astrophysicist Frank Drake, would be made of tightly packed nuclei instead of standard atoms forming atomic particles. Their lives would be incredibly short due to rapid atomic reactions. If they existed, they would only live for a few moments and could only be visible under a microscope. But then, let us consider the opposite. What if there are enormous creatures in the universe, observing us as we observe microorganisms under a giant magnifying lens? How large might these creatures be? The size of elephants, or even bigger, perhaps the size of an entire sea, a planet, a world, or even a cluster of galaxies. Maybe they include the entire universe. Life might not necessarily depend on particles and atoms, but could be intricately intertwined with the very fabric of the universe. According to this idea, life is ubiquitous, existing in a constant way surrounding us. This concept challenges conventional assumptions and invites us to contemplate the fundamental nature of life in the broader context of the universe. Which idea resonates most with you? Share your thoughts in the comments below. If you found this video fascinating, stay tuned for more captivating cosmic discoveries. Thank you for watching.